So our next speaker is Gleb Arutyunov with the talk Aromatric Structures for Classical and Quantum Ruijsenaars-Schneider Models. Please.
Thank you. Yeah, first of all, let me say that it's my distinct pleasure to greet my teachers, colleagues, and friends, and to wish them strength, optimism, and of course, new horizons, reaching new horizons in physics and in life. So quite some time ago, together with Lerner and Serezha Frolov, we have developed the R matrix quantization scheme for elliptic Ruijsenaars-Schneider model. And well, as you have seen, the models of Calogero-Moser type were a current topic of this conference, of this wonderful conference. And it therefore quite natural that I was motivated to also talk about some developments and some new results in this field. And one of the important tools which we have used to put Ruijsenaars-Schneider model in the framework of the inverse scattering method was a reduction scheme, or simply reduction. And in this approach, we start from an initial phase space, which is sufficiently large phase space. And we start with some relatively simple Hamiltonian system, which exhibits a certain amount of symmetry. And then reducing this initial large phase space under the action of the symmetry group, on the smaller space, we obtain some non-trivial integrable model, like, for instance, Ruijsenaars-Schneider model or Calogero-Moser model. I hope you can still see me. Can you see my slide?
No.
It disappeared for a second, but now I think it restored, no?
No.
No.
Because I see, I think sharing disappeared.
Try to share it again.
You share, but not your presentation.
I'm sharing, but not my presentation. Let me see how to.
Try to restart your sharing.
If I would know where to click here.
Oh, Gleb, you are not teaching by Zoom. Not you.
No, I'm teaching not by Zoom, exactly. I'm teaching by my personal presence. In personal, yes, I'm teaching what is.
Okay, so just stop sharing the screen.
Stop it for you, and you.
You stop it for me now. Okay, very good.
And now share it again, but with a window with presentation, where it's PDF or whatever. Acrobat.
Can you see it now?
Yeah.
Yes.
Okay, I do it full screen. I hope you can see it.
Yes. Now
okay.
Yeah.
Very good. Very good. So, in particular, if we are talking about Ruijsenaars-Schneider models with various potentials, say rational or hyperbolic or elliptic, then one of the natural initial phase spaces to start with could be a cotangent bundle to a Lie group. For instance, you can think about this group just being GLNC. And for the case of a rational potential, it's just the usual cotangent bundle. It's a semi-direct product of a group G with its Lie algebra. When you move to a more complicated model, to a hyperbolic one, then the cotangent bundle gets replaced in this scheme by the so-called Heisenberg double, which is a symplectic manifold, topologically been just a direct product of two Lie groups. And in the case of an elliptic model, the phase space to start with could be so-called affine Heisenberg double, for instance, where you take the double and just consider affinized Lie group. Well, in some cases, it's also possible to construct directly a quantum reduction, starting from the quantum version, say, of the cotangent bundle. For instance, this can be done for the case of a rational model. And in this case, just reduction reduces to a certain problem of factorization in algebra. And let me say that, of course, many our colleagues, some of them are present in this conference, who contributed in developing this nice scheme, starting from the paper 1978 by Kazhdan, Kostant, and Stenberg about Calogero-Moser system obtained by reduction of the cotangent bundle to Lie algebra. What I would like to talk today is the generalization of these models when you include new degrees of freedom, or spin degrees of freedom. In this respect, I would like to refer to the talk by Kolyar-Reshetikhin, where also spin Calogero-Moser system was considered. In this case, the natural phase space to start with is an extension of the cotangent bundle, say for the rational case, where you extend it by a number of copies of the coadjoint orbit of the Lie group G. And it was mentioned in the talk by Professor Olshanetsky, including of coadjoint orbits means that you introduce in the system new degrees of freedom, in particular, well, spin degrees of freedom. And this system works, or this scheme of obtaining the Ruijsenaars-Schneider model with spin and with rational potential works well. But the question is that when we come and we would like to construct a similar model for the case of a hyperbolic potential, we have to think what to use to replace coadjoint orbits. So what would be a manifold which should replace the coadjoint orbits which were used for the case of the rational potential? Well, in this case, we are talking not about the Hamiltonian reduction, which was in the previous rational case, but we are talking about the Poisson reduction. In this case, this manifold, which is supposed to replace a collection of the coadjoint orbits, should naturally carry the action of the Poisson-Lie group G star, which is a Poisson-Lie dual of the group G, which was used to build up, say, the Heisenberg double. So far, the progress in this direction was done for the case of the hyperbolic model, and that is what I would like to explain in today's talk. So I would like to explicitly describe what should be replacement of the coadjoint orbits and how the reduction scheme should be performed in order to get the hyperbolic Ruijsenaars-Schneider model with spin. And if time permits, I will also tell about some arithmetic structures for the quantum case for the hyperbolic Ruijsenaars-Schneider model, but without spins. So in a sense, that would be a justification of my talk concerning the title of the conference. So the first part will be a bit about geometry, and the second part will be about quantum integrability. I had an opportunity already to talk about this stuff somewhere else. So for those who have heard my talk already, my apologies. Okay, so this is basically what I would like to talk. So I split my talk into two parts. First, as I said, there will be classical models with spin. And for that, I need such a manifold as Heisenberg double, and then a replacement for coadjoint orbits which I will describe explicitly. This would be the so-called oscillator manifold, as you will see. Then I will talk about reduction and also about the subject of superintegrability. So these models are superintegrable precisely in the same sense as Koller-Reshetikhin explained in his talk. And in the second part, if time permits, I will talk about quantum hyperbolic Ruijsenaars-Schneider model and also introduce some new presentation for integrals of this model and show their relation to, of course, well-known McDonald operators. Well, this work is based on two papers which I've written with my former PhD students, Enrico Levucci and Rob Klabers. So let's talk about classical models with spin. So let's start from equations of motion of spin Ruijsenaars-Schneider model. So this is a model of n particles on a line. And to each particle, we associate spin variables A and C. For particle with an index I, we associate two vectors. Well, these are polarization vectors. A and C, where index alpha describe various polarizations, and it runs from 1 to L. Equations of motion for this model have been written by Krichever and Zabrodin in 1995, and they were obtained by looking at the dynamics, by analyzing the dynamics of poles of the non-abelian two-dimensional Toda theory. In the general case, the potential is elliptic. It's written explicitly via Weierstrass zeta function. And of course, it can be degenerate to the rational case and to the hyperbolic or trigonometric one. Now, in this model, the variables A are constrained. Namely, they must satisfy the requirement that summing up all polarizations for a fixed index I, the sum must be equal to 1. And in this theory, it's also very convenient to introduce the so-called collective spin variables by making the quadratic combination AC and summing over the index alpha, this collective spin variables. Now, although equations of motion for this model were written down explicitly, the question about the Hamiltonian structure appears to be rather non-trivial. So what one has to do, one has to find the Hamiltonian and the Poisson bracket such that these equations of motion are reproduced as Hamilton's equations. And this is where the reduction scheme is useful, and which allows to actually construct the Hamiltonian formalism for this model. So we have done this in the past with Sergei Frolov for the case of the rational model, rational potential. But the question about the hyperbolic model appears to be rather non-trivial. In particular, what is the Poisson bracket should be between the variables A and C. And the answer to this question I would like to show you. And as you see, it will be quite non-trivial Poisson structure that is behind that is standing behind the spins. It would be extremely difficult to guess it just by looking at these equations, but fortunately we have the reduction scheme as a guide, and this will allow us to build up explicitly the corresponding Poisson structure. So in order to proceed, I need to introduce the Heisenberg double. First of all, this is a basic phase space which is responsible for the particle dynamics. And I will start then from the factorizable Lie bialgebra. Factorizable means that this Lie algebra is applied with a bilinear non-degenerate odd invariant form, which allows to identify G star, the dual space to the Lie algebra, with the Lie algebra itself. And the Poisson, the commutator on G star is defined with the help of the R matrix cos cycle on the Lie algebra G. The double first one introduces the double as a vector space. It's a sum of two copies of G. Then there are natural embeddings of G and G star into the double. So the Lie algebra G itself is embedded as a diagonal subalgebra. And G star is embedded with the help of projections constructed with the help of R hat. R hat is built up with a split solution of the modified classical Yang-Baxter equation. And this is a standard story of how to embed G star into the double. Then we can build up the double Lie group, which is in this approach is just a direct copy of two, is a direct product of two copies of a Lie group. And the group G star, which is a Poisson-Lie dual of G, is embedded in the double also by means of raising up this factorization with R plus and R minus, with these projections R plus and R minus to the Lie group. So G star is represented inside of double by its two elements, U plus and U minus, where U plus and U minus belong to the Lie group G. And I assume that there is a diffeomorphism, sigma, which is diffeomorphism of G star and G. And I assume that the factorization problem of factorizing element U into two copies U plus and U minus has a unique solution. So sigma sends U plus and U minus into unique element of the group G, and that's the diffeomorphisms between G star and G. So this diffeomorphism will become important for me in what I'm going to discuss later on. Now, the Heisenberg double is a symplectic manifold. In the case I'm going to discuss, I will assume that I'm talking about the double of GL and C. So A and B here are two GL and C matrices, and the entries of these matrices provide for me a ring of coordinate functions on the double, and on this ring of coordinate functions, the following Poisson structure is given in terms of two R matrices, R plus and R minus, where R plus and R minus are solutions of the classical Yang-Baxter equation. The difference between R plus and R minus is a split Casimir. So R plus and R minus are two standard solutions of the modified classical Yang-Baxter equations associated with the group GL and C. Okay, so this Poisson structure, you can also think about it as a 4-cross-Lie Poisson structure on a torus with one fixed point, and this is a Poisson structure for holonomies around the cycles of the torus. Good. Now, the Heisenberg double is a manifold which carries a symmetry. In particular, if we supply a Lie group G with a Poisson structure given by Sklenin bracket, then the group G acts on a double, and the action G cross D into D by means of similarity transformation is a mapping of Poisson manifolds. So group Lie acts on this manifold in a Poisson way. This Poisson action possesses a non-abelian moment map. This moment map is given by an element of G star, in other words, by a pair M plus and minus. And this pair M plus and minus, with the help of the diffeomorphism sigma, which I have just discussed, can be modeled by an element of the group G by taking this element M, being M plus, M minus in the power minus 1. In terms of the original dynamical variables, in terms of these matrices A and B, this element M is given by this quartic combination BA minus 1, B minus 1, A. Now, so the moment map in this way can be treated as an element of the group G through this diffeomorphism sigma, and the Poisson bracket between components of the moment map is the so-called Semyonov-Tenshansky bracket, which is a bracket which is a Poisson-Lie structure on G star, written under diffeomorphism sigma as a new Poisson structure on the group G, and it's explicitly given by this Semyonov-Tenshansky formula. Now, the double has an involutive family, family given by traces of powers of the combination BA-1, or alternatively A-1B. Good. Now I'm coming to the question, what would be a natural replacement for the collection of the coadjoint orbits for the case of the hyperbolic model. So for this, I need to introduce pairs, in particular NL pairs of canonical variables, A and B, which you can think about as entries of two rectangular matrices, AI alpha and B alpha j, where I and j runs from 1 to n and alpha runs from 1 to L. And so these are rectangular matrices, and on the coordinate ring generated by entries of these rectangular matrices, you can define a couple of Poisson structures labeled by plus and minus. And these Poisson structures are written with the help of two R matrices. One of them is the matrix R, which is familiar from the previous construction of the double. So R is a solution of the skew-symmetric solution of the classical Yang-Baxter equation, and rho is a similar solution, but it's associated now with spin degrees of freedom. So it's built up with the help of matrix unities E alpha beta, where alpha beta are running from 1 to L. You can also introduce a notion of rectangular, well, if you want to call it a rectangular split Casimir. And as you see, the brackets, say, between A and B appear to be, in a sense, inhomogeneous. They involve just rectangular split Casimir. So these are terms which are constant terms. They do not depend on the variables A and B. And then there are, on the top of that, there are quadratic terms. So in particular, you see that if you send kappa to 0, where kappa, you can think about this as being a deformation parameter, then in this case, the brackets just boil down to NL pairs of canonically conjugate variables. And these are precisely variables which you can use in order to build up the orbits of minimal dimension for the case of GLNC. By taking these collective spin variables, you can describe the Lie algebra, the orbits of minimal dimension in the Lie algebra GLNC. And this is precisely what has been used for the case of the rational Kalogera-Moser model, of the rational Ruijsenaars-Schneider model, and now introducing this quadratic deformation of this oscillator algebra. The claim is that this Poisson manifold now becomes the proper manifold in order to describe the spin degrees of freedom for the case of the hyperbolic model. Now, out of these variables A and B, we can construct n cross n matrix omega, just by adding with identity the combination AB. So AB here, summation over index alpha is assumed. So AB is a matrix n by n. And what is important for me is that on this Poisson manifold, oscillator manifold, as I call it, we have an action of the same Poisson-Lie group G. And it acts on the oscillators A and B in a bit intricate way. So first of all, with an element omega, you define an action of an element of G star on a Lie algebra element X, and then X itself acts on the corresponding oscillator A or B. And from the point of view of this action, this is just an example of a tracing transformation. So the group G star acts on the Lie algebra G by tracing transformation, and then the result of this act on the corresponding oscillators. And there are two important things which you can discover concerning this section. First of all, this section of the Lie group G appears to be Poisson. So, and the second, that this action has a moment map, and the moment map is given in by element omega in the following way. So first we have to factorize omega into components omega plus and omega minus, which provide for us an element of G star, and then we have to take an inverse in G star, and if we wish, we can then map it again to the group G, forming this element eta. And eta then has the same Poisson bracket as Semyonov-Tietzhansky bracket, and you can check that this is precisely the moment map for this Poisson action on the oscillator manifold. So now, well, in addition, just to mention that in addition, we have another action, which I call the action of the spin group. In addition to GL and C, which could be naturally called the particle group, there is also a spin Poisson-Lie group, GL a little c, which acts on the oscillators A and B in a simple way by just multiplying A and B from the other side, either from the right for A and from the left for B. And this action is also Poisson, provided you supply the group GL a little c also with a Schlanian bracket. Okay, so we have a nice oscillator manifold, and we have the Poisson-Lie. We have Poisson action on this manifold of two Poisson-Lie groups. One of them is a particle group, and the other is a spin group. And now, what I would like to do, I would like to consider the Poisson reduction of the combined manifold, namely the Heisenberg double cross this oscillator manifold by the action of the particle group. And for that, I need to recall a little bit about how such a Poisson reduction can be done. This is a theory which has been put forward by Flashka and Ratiu, 1996. So if we have two Poisson manifolds, say M1 and M2, and we consider combined manifold, which is just direct product, and then we also assume that on each of these manifolds, we have an action of the Poisson-Lie group G, and such an action gives rise to two moment maps, say, associated with the first action and with the second actions, and this moment maps we label as M1 and M2. And then on this product manifold, we can build up a new action of the group G by just taking the product of the moment maps M1 and M2 and allowing this moment map to generate an action on the product manifold. From the point of view of individual actions, the corresponding vector field becomes a bit complicated. It's not just a sum of two actions because moment maps are non-abelian. M1 and M2 as elements, say, of G star, they do not commute with each other. It leads to a bit unusual action on the product. Well, you see it explicitly from the formula for the corresponding vector field, namely, say, on the second manifold, the action starts to depend on the moment map of the first manifold. Nevertheless, one can show that the map from the Lie algebra to the Lie algebra of the vector fields acting on the manifold map on the manifold M being the product of M1 and M2 is a Lie algebra homomorphism. Now we can apply this theory, so we can take as our product manifold the Heisenberg double cross the oscillator manifold, one of them say sigma plus, or we can take equally well sigma minus. And then we need to impose the moment map equation. Moment map on the product is given by M star n, where star means that we consider the product of this moment maps for G acting on the double and G acting on the oscillator manifold as a product in G star, because M and N, strictly speaking, they are elements of G star, so we need to multiply them as elements of G star. And we then say that we fix this moment map to be proportional to identity, so T is just a number, T is a coupling constant. Explicitly, if we write this equation, then it becomes a statement that the moment map of the double MA minus 1B minus 1A becomes proportional to an element omega, and proportionality coefficient is a coupling constant T. So all we need now to do is to solve this matrix equation and factorize solutions over the action of the group G, because the stability group of the moment map coincides with the group G itself, since on the right-hand side of moment map we have an identity. And what is interesting is that if we now reconsider, according to the Flash-Karatyuk theory, the action of the group G on the oscillators A and B, this action becomes, of course, complicated according to what I told you. Now, the double is involved in the transformation properties of the oscillators. You see it explicitly from appearance of the moment map M of the double in the corresponding transformation of oscillators A and B. But fortunately, if you are talking about restricting this action on the solutions of the moment map on the hypersurface given by the moment map equation, then you realize that precisely on this hypersurface, this complicated odd star omega star M minus 1 action becomes ineffective, because the corresponding element is simply the left-hand side of the moment map, which is proportional to identity, so the action becomes ineffective, and it reduces simply to the standard transformations of a vector by a matrix from the left, either from the left or from the right. But this means that if you would like to describe the solutions modulus action of the gauge group simply acts on the constrained surface by multiplications from the left and from the right. So all what you need is to construct G invariants of this action, and this would provide for you simply description of the space of solutions in terms of invariant variables. How to do this? This we know from the experience with the rational model. We take these elements A and B and we factorize, like we diagonalize A with an element T, and then element B comes to be written with the help of additional matrix U and diagonal matrix P. So Q and P are two diagonal matrices. And in order to make this factorization unique, you need to restrict T and U, and this restriction can be achieved by imposing on T and U conditions, namely, say, taking T and summing from 1 to n over index J. You require this to be 1, and the same is for U. And this defines elements T and U as elements of the so-called Frobenius group. So T and U defined in this way, they they belong to a group, and this group is known as a Frobenius group because, well, there are reasons for that. This group has a Lie algebra which possesses a non-trivial Tuka cycle, which possesses a Tuka cycle, and in this case, it can be called Frobenius. Now, in order to keep this Frobenius property of factorization of A and B, you also need to introduce a diagonal matrix Z, just constructed from T and A. And then you introduce invariant spin variables A and C by taking combinations of spins A and B and tracing them with the help of these dynamical variables coming from factorizations of A and B. So these both A and C are invariant spin variables. And on the top of that, you can also introduce the matrix L, build up with the help of all ingredients which we have, and this L will become at the end the Lux matrix of the model. And so things are arranged in such a way that the original moment map simply becomes the moment map equation simply becomes an equation for the Lux matrix L. And the explicit solution is given in terms of, well, this formula you see, this is the last formula here at the bottom of the page. Very good. So now you have everything at your disposal. So you have the invariant spin variables, and you know how this is represented in terms of original, yeah?
Gleb, may I have just a short question? So with this A and B, do you have a closed Poisson algebra for those?
For A and
for the pair A and B.
Yes, and this is algebra is this one. This is a algebra. It's a closed Poisson algebra. All the Poisson brackets satisfy Jacobi well as it should be. Yeah, this is
I see.
So this is a Poisson manifold, which I call oscillator manifold. Then you build up invariant combinations, invariant spins in a sense that they are invariant with respect to the diagonal action of the particle group. And then you go and compute their Poisson brackets. And they appear to be quite complicated. This is a result. This is a result. It's written in terms of several R matrices. And just to appreciate it, let me say that the bracket on the right-hand side is nonlinear. So it involves spins up to quartic terms, up to quartic. It's quartic in spins. That's an element Y. Which appears to be y12. You see it's quadratic in the variables A, and then spins this y is also dressed. Say it appears on the right hand side of the bracket C1 and A2, and you see then the result is a quartic structure. Of course, to guess it just from scratch, it does not seem to be possible. Well, you can see it also explicitly. I have written down for you quite explicit formulas for this Poisson algebra. So all the Poisson brackets are satisfied. And yes, if you are talking about the Poisson bracket of the Lux matrix, then this is a quadratic Poisson algebra. For the Lux matrix, and the R matrices are dynamical, so they do depend on the coordinates, but they also involve shift by spin variables Y. So Y is a matrix which explicitly depends on spin A. And that's interestingly, this appears to be different from the spinless case. When you don't have spin.
Sorry, we have 3-4 minutes left.
Yeah, okay, very good. So then probably I will not be talking about the quantum situation. Yes, I was anticipating the quantum thing. I just left it, yes, if I will have time. So maybe I will just finish with telling you something about superintegrability of this model. So superintegrability, yes, it's precisely in the same sense as in the talk of Koller-Reshetikhin. We have a commutative family, HM, which comes from the double. But on the top of that, we can introduce non-abelian integrals. I call them Gn plus and Gn minus, and they involve not only elements of the double A and B, but also spin variables. Spin variables S, which can be combined in these elements S alpha beta ij, and then trace is taken over indices I and j, and alpha and beta, these are free indices. So J plus and G minus are L cross L matrices. And then you can show that before the reduction, the integrals HM commute with this J plus minus. And of course, they continue to commute up after the reduction. And this J plus and G minus can be also written in terms of invariant spin variables, or variables on the reduced phase space, if you wish. And this is how they look like in terms of matrix and matrix S. Then you can build up and compute the Poisson algebra of these integrals. It's a non-abelian algebra. In particular, if you restrict yourself to the modes, to the zero modes, G0 alpha beta, then the Poisson algebra simplifies. So it's closed. Zero modes form a closed subalgebra. And if you introduce an element omega, which is just G alpha beta plus kappa G0, then you realize that these omegas, the Poisson bracket for the omegas, is nothing else than the Semyonov-Tinshansky bracket. So omega appears to be nothing else as a moment map for the Poisson action of the spin group. So spin group essentially becomes a symmetry group of spin variables, and this symmetry, this Poisson-Lie symmetry, being combined with commuting integrals, altogether they provide a symmetry and integrals for the combined model with spin. What else should be said? You can also introduce a generating function for these integrals, and then you see that these integrals can be then written as a deformation of the affine algebra, quadratic deformation of the affine algebra. So Poisson brackets are of course satisfied. And so this is the way how symmetry algebra of non-abelian integrals of the spin Ruijsenaars-Schneider model looks like. And maybe the final comment is that using the projection method of Olshanetsky and Perelomov, you can solve equations of motion for this model with spin in an elementary way. You just start from the equations of motion in the double and the trivial equation of motion for spins, and then you just use the factorization, which I described above, factorization of A and B into elements of the Frobenius group. And in this way, you can elementary solve the dynamical equations for spin variables. They essentially, what you need to do, you need to take the initial data, initial coordinates, evolve them with a Lax matrix at zero, taken at zero moment of time, and then the result would be a matrix which you need to factorize. You need to diagonalize by an element of the Frobenius group, this capital T, and this element capital T, depending on time, is then something which defines the evolution equation, defines the evolution of the invariant spin variables A. So this is the way how this model is solved. It's solved in an absolutely elementary way by using projection method. Okay, I think with this probably I will stop, and I would like once again to greet our jubilars, Nikita and Lenya. Thank you.
Thank you.
Thank you. Yeah, thank you. We're quite short on time, so maybe one or two short questions.
I have a longer question, but we can discuss maybe on
to
the
your long
day.
question. I can give a short answer.
No. I mean that possibly the next speaker will be also interested in it, Volodya Rubtsov. So we can discuss on the coffee break. But just now, very short question. So how is this algebra that you described, B and A, related to Fock-Rossley?
This A and B, you mean this is?
Yeah.
That's I don't know. I have no idea. This algebra, you see, it's not homogeneous. It's a deformation of the standard oscillate of canonical conjugate variables. But if you build up from this A and B the quadratic combination omega, this one, then omegas between themselves satisfy Semyonov-Tenshansky bracket. So basically, what I have done, I have found an oscillator description of the Semyonov-Tenshansky bracket, and Semyonov-Tenshansky bracket is a quadratic deformation. You can think about this as being quadratic deformation of the Kirillov constant bracket on the coadjoint orbits. So in one case, yes, Kirillov bracket.
But that's what I want to discuss. How it's so related to networks and all this stuff. Okay, but that we can do after.
Then we can do it afterwards. Yeah.
Good.
If there are, we can do one more very short question.
Is it possible to generalize beyond GLN, all this construction? Or is it hard to do?
I hope so. I hope so, but we have not done this. I think it's possible. Actually, it's also possible to generalize this construction or reduce this construction for the case of not GLNC, but for the explicitly real case. For that, you may start from the cotangent bundle, well, not cotangent bundle, but double of the unitary group. And actually, this has been done, I have to cite in this respect, by the work of Laszlo Fehr. And yeah, I think I have a citation somewhere a little bit later on when I was discussing further developments. Yeah, this has been done by Fehr, and Marshall. That concerns an explicit real case. So what you would do for the real case. But that's an interesting question, how to do it for other groups. Should be done somehow.
Okay, thank you again.